Good morning, everyone. Welcome to the third Start Kubernetes live stream. Today we'll talk about configuration, container patterns, and application health, the health of the applications that are running in your Kubernetes cluster. In our first stream, we covered the Kubernetes introduction. We talked about pods, replica sets, deployments. Last time we talked about services, the ingress resource, jobs and cron jobs. And today, as mentioned, we'll talk about configuration, container patterns and init containers, and application health. Okay, so let's get started. So this is the agenda for today. There will be, I think, let me check, 6. There are 6 labs, 6 demos that I'll go through. And as mentioned, we'll talk about configuration, specifically ConfigMaps and Secrets, and then we'll go into init containers and container patterns, and then application health. Okay, so I don't know how many of you heard about or heard of the 12-factor app. Not gonna spend too much time on this, just want to mention it that it is a manifesto that was created by engineers at Heroku around 2011, and it was derived from their best practices and things that they noticed as they were building SaaS applications. Now, cloud development has evolved since this came out, but the principles still apply, or they can be at least used as a baseline. So one of the factors from the 12-factor app is application configuration, or talks about application configuration, specifically about storing the configuration in the environment instead of hard coding it inside your services or inside your applications. So I think it's the third factor. So if you go to 12factor.net, you can see all the 12 items there. Now, in most cases, the application configuration will vary between different deployment environments. For example, when you're running your application in testing or staging environment, it is highly likely that you want your application to use different databases or different backing services or other services from testing. You want to use your testing databases, your testing services, and from the prod you want to use the prod database, prod settings, prod configuration. So your configuration is tied to the environment as well. So you don't necessarily want your apps from the testing environment to talk to your production database. That would be really bad. Now, another reason for separating your code from your configuration is that you don't want to rebuild your application each time you change a configuration value. So that would be a massive waste of time and resources. So instead, what you should do is you should always deploy the same application or the same binary, but then augment the application's behavior using configuration that's specific to the environment your application is running in. So you build the binary once, and then you attach different configuration for your test environment, for your prod environment, and your app knows how to run in that environment with that configuration. Typically, configuration is anything that your application needs to be able to start and run. So a couple of pretty common or standard configuration settings are any connection strings you might have to databases, connection strings to queues, or any other connection strings to other services. There's also credentials, usernames, passwords, keys, certificates, API keys. And then you have things like port numbers, dependent service names, and like different addresses. Now, at a high level, we could separate these configuration settings into 2 groups. We can say one group is non-sensitive configuration values, and the other group is sensitive configuration values. So the non-sensitive group, as the name implies, contains everything and anything that you don't necessarily consider to be sensitive information. So you're not going to be You're not going to be embarrassed, or it's not going to pose any security risk or anything like that if the information is leaked. So things like port numbers, service names, even connection strings, assuming they don't contain any usernames or passwords or any public APIs and things like that. Now, the second category contains sensitive information or secrets. So these are things like passwords, API keys, any application secrets, credentials, certificates, etc. So pretty much anything that can severely compromise your application or your system if this information gets out. So in Kubernetes, there's a resource called ConfigMap, and ConfigMap can store configuration values, key value pairs. So these values can then be consumed or mounted to containers inside a pod. Either inside, you can mount them in the pod, or you can use them as, let's say, command line arguments or environment variables or like read-only files. You can also read and use them through the Kubernetes API as well. Now, one note here is that Kubernetes API config maps need to exist before they're consumed by pods, unless they're market optional. So if you have a pod that's referencing a config map and you try to create that pod without that config map actually existing, you'll get an error, right? So you need to create the config map first and then create a pod that's going to use it. Also, the config maps need to be in the same namespace as the pod in order for the pod to be able to use it. So here's a quick representation, YAML representation of a config map. This specific one stores single values. So line 7 and 8, we have a value called, or rather a config setting called port number, and then we have a config setting called name. And then on line 9, you can also store values that they look like fragments of a configuration file. So in this case, we're calling that key settings.env, and then we have a multi-line string, which is basically two values or two variables with two values. So you create this, you deploy it to your cluster, and then how do you use this? So one way to use this is you can set the configuration values that are defined in the config map as environment variables. So the way you do that is you use a field called value from, and that one just specifies where your value is going to be coming from. And if you look at the line 5, we're saying it's going to be a config map key reference. So we want to reference a config map. And then we're just saying this is the name of our config map, and this is the key whose value we want to store in the environment variable called first name. So the same goes for the port number. So we use config map key reference to reference the config map, and then reference a specific key or specific value inside that config map. So we also have this settings.env here on line 9. So how about these? So here's a way that you can bring in the file from a config map. So what we did here is, and this is just a snippet, we created a volume that's called config. So that's on line 7. And what then that volume is created from a config map that's called simple config. And then under the field called items, we're just specifying this is the key from the config map. So settings.env was the key that we used in our config map. And then we're saying path for this file should be local.env. So what this does is it will mount this settings.env item to the path called local.env. So the process of mounting this volume will create this local file that will contain the key value pairs that we defined under the settings.env from the config map. Then on line 2, using the volume mounts field, we can then include or mount this config volume under a specific folder inside of the container. So in this case, we are on line 3. we're referencing the volume that we defined on line 7. And then on line 4, we're saying mount that volume under /config folder and then mount it as read-only. And we'll see in the lab and in the demo, I'll show how this shows up. But if we would go into that specific container, right, we would go into the config folder, we will see that local.env file created, and the contents of that file will equal to the contents of the settings.env, which came from the config map. So the way to create the config maps, you can create it from the YAML, of course, right? You create the YAML, deploy the YAML, but you can also use Kubernetes CLI to create your config map. And there's 3 different ways that you can do that. First one is using the from literal argument or flag. So you're going to say Kubernetes kubectl create CM. It's a short name for config map, name of the config map, and then you do -- from literal and equals key equal value, right? So you provide the key value pair you want to create. Second one is environment files, like if you've done any applications or any websites or pretty much anything, you've probably heard about environment files, right? It's just plain text files that have key value pairs in them stored as, and those get usually run as environment, they're set as environment variables in the environment. So you can use, instead of using from literal like 500 times or 10 times or how many environment variables you have, you can use from env file and then just point to that specific file, and it will create the values for you in the config map. Finally, you can also use the from file flag, and this one will just create a config map from the contents of a file. So in this case, we have a simple JSON file, and we can use from file, and we'll get the configuration, that JSON configuration in the config map. All right, time for the first demo and the first lab. So this will be about config maps. Let me just switch to this guy. Perfect. All right, so I have a cluster running, Kubernetes cluster. So what I'll do first is I'll just create a simple config map, the one that we used in the slides. So I'm setting the kind to config map, naming it simple-config, deploying to the default namespace, and then under the data field, I'm setting the port number to 8080, setting the name, and then setting the settings.env file as well. So let's create this. Okay, and then just like with any other Kubernetes resource, we can describe the resource. And you'll notice it has the name, it has the namespace, and then down here under the data, you'll see there's settings.env that has these 2 variables. There's a name, which is set to this value, and then a port number that's set to 8080. All right, so now that we have this, you can also list it like this. Now that we have this, let's create a pod and then see how we can consume this from within a pod. So I'm just creating a pod directly. Config pod, just a BusyBox container that's going to sleep. And then I'm setting the environment variable. So what I'm doing here is I'm referring to the simple config map that we've created, and then mapping a specific key from that config map to a specific environment variable name in this container. So let's deploy this. Let's make sure that this pod is running. Okay, so pod is running. So what I'll do now is I will get inside this pod. So I'm within the pod, the config pod that we've created. And if I run the env command, this will list me all the environment variables. You'll notice that the host name is set to config pod, which is just saying that we're inside of a pod. And then you'll notice there's the port number here. We have the first name here as well. So we basically mapped those 2 values from the config map as environment variables. So you could imagine if you had had an application running here in your container, then your application could read these values from the environment as needed. So we have these two. How about that file? So let me delete this config pod here. Oh, I actually have to say that it is a pod. And then what I'll do is I'll create a volume, and then I'll mount that volume inside of the container. So I will get that settings.env file as an actual physical file inside the container. So as soon as this pod goes away, let's see, still being terminated. Okay, hopefully soon. Or I can just rename the config pod again and use. Oh, okay, it's deleted now, terminated. So let's do. Whoops, that's not good. Actually, I have to do it this way. All right, so this is the same pod. These two environment variables are exactly the same. The new thing that we added is this volumes thing. And I know I haven't talked about volumes yet, and that will be probably coming next week. We'll talk about stateful applications, and then volumes, persistent volumes, and all those things. So we're creating the volume here, calling it config map, and the source of data of the volume is this config map with, as we say, this is the key from the simple config map, and we want to store that settings.env as a local.env file. And then up here in the actual container, note that the volumes are defined on the pod level, not on the container level, and that's because no matter how many containers you have in a pod, you can reuse those volumes, right? Those containers can reuse and mount any volumes that they want. So inside this container, we have this single volume mount that mounts this volume that we've created under the /config path, and it's setting it to read only. So let's create this. And once this pod is up and running, perfect, we can go back inside the pod. And then you'll notice that there's the config folder here. And then inside this config folder, there's the local.env file. And this file actually contains those two values that we created in the config map. So in these previous two examples, what I've done is we've set the configuration settings as environment variables, and then we mounted this settings.env file as a volume. So what we could also do is, instead of, like, let's say you have a lot of configuration settings, right? You don't necessarily want to mount each specific thing. So instead, what you could do is you could just mount the contents of the config map. So anything that's in the config map, you can map it directly. So let's see how to do that. And of course, we'll map those as files, right? So we'll create a volume from the config map, and then we'll map that volume to the specific folder. So let's do this. For some reason, this is being extremely slow today. Okay, let's do cat here. All right, so config pod -1, and this is the same as it was before, right? The only thing is that we're not explicitly calling out the items that we want to map, right? We're just saying, just bring in the config map as this volume, and then we're bringing it into the /config folder. Okay, so this one is running, so I can execute inside this one, bin sh, and then under config folder. So what will happen now is all those three values from the config map will actually be mounted as files. So if I list the port number, notice I get back 8080, same for the name, and then same for the settings.env .env. So what happened here is it just mapped all the values from the config map as files inside of the container. So another thing that you can do is, let me delete this guy, pod 1. We can do the same thing with environment variables, right? So this, the previous example showed how to map everything as files, but you can do the same thing and map the values as environment variables. So let's do that. Okay, so we can call it config. Well, I can actually call it configbot, right? Okay, so let's do another pod here. Oops. I should seriously create an alias for this, typing it so often. Okay, so this time we're just saying, instead of env, we're saying env from, right? We're telling the container, hey, get the environment variables from this specific config map, right? We're referencing a config map with this name, but also add this prefix, right? So this, we're just saying add the simple underscore config underscore to prefix to all environment variables that, to all the values from the config map that you will create as environment variables. Okay, so let's, at least it's very fast to run, so that's good. Okay, so let's go in, and now if I'll clear the screen and run the environments. So you'll notice that there's simple config underscore settings.env. Now this is a little bit of awkward because it's actually like a multi-line string. And then down here, you'll see the simple config underscore name, and there should be one up here, simple config port number. So this is just a way that you could map all the configuration values from a config map without picking and choosing which one you want to map. So question, which approach is preferred, map settings and as environment? So I would always go as files because with environment variables, what can happen is sometimes when, like depending on what your application is, right? But let's say in a lot of cases when something goes wrong with an application, right? You want to get all the logs, you want to get all the environment variables, right? You want to get all those things, right? So sometimes that may cause your logs to leak, right? Or might cause your logs to contain information that you don't necessarily want it in there, right? So if you have it as environment variable, that's one thing to keep in mind. It is much easier, I think, to do it, to just read it from the environment variables, at least if you're doing like, I would say pretty much any programming language, right? It's easier to read it as an environment variable than a file. But again, it all depends. For configuration settings per se might not be such a big deal, even if it's an environment variable. However, if you're doing like secrets that I'll talk about next, right? Secrets as environment variables, you should not be doing that, right? Because that's when that leaking inside your logging system or something, you might save a password or save an API key that you didn't necessarily want to save in your logs. But yeah, again, for configuration, up to you, what you prefer. Files, I mean, I would probably go with like a JSON configuration file, have it everything in a single file. Your application reads that, parses it, or do environment variables as well, but just make sure you're not actually storing anything, or make sure you don't leak the environment variables into your logging system. Okay, so let's also look at a couple of options how you can create the config map from using kubectl. So you can do literal config from a literal equals port number, let's say 5000, right? So this will create the config map. And if we get the config maps, this is the one. And then let me, this is the YAML representation. It's basically same as if we would created it from YAML, right? Then if we have like a file, so let's say prod.env, right? So let's say we have some environment file, and then we can say the service http something.com, whatever. You can imagine some environment variables here. And we have these in prod.env files stored like that. If you want to create, like one way that you could create a config map with these two values is to do from literal, and then we would do port, right? And then from literal again, right? Blah, blah, blah. So instead of doing it that way, you can just use from env file and then say kubectl create config map, environment config, and then from env file equals, and the file name is prod.env. So now if we describe this one, describe cm env config, you'll notice that we have port 8080, and then we have the service something.com. So kubectl will parse this environment file and then create a separate key value entry in the config map for each line in your environment file. And then finally, if you have like a config file, for example, so let's say we have config file, some JSON, this could be XML, it could be whatever your application supports. And we'll say service http blah.com. Okay, so let's save this guy. Okay, so we have this JSON file, and then we can say create config map from file, config map from file equals cfg.json. And now if I describe this one, describe from file cm, you'll notice that it has the same or similar entry as that settings.env in the first example, which is just the contents of the actual file that you've provided with the from file, right? So, so if you have like a configuration, JSON configuration or YAML or XML or wherever you store your configuration, this is probably the easiest way to do it, right? Just create everything from a single file, assuming your application already knows how to parse that file and use it. And this is how you can easily bring it inside Kubernetes. All right, now it's time for you to try the config maps. So I'll do 10 minutes, and then we'll come back and we'll talk about secrets, and then it'll be another lab really quickly after that. So let's do 10 minutes, and I'll post the link. The link should be, just go to live.startkubernetes.com. I think there should be session 3, yep, and then config maps lab. All right. See you back in 10 minutes. All right, any questions on configuration maps before we continue? Also, I'm hoping you all are actually going through the labs. Let me know if you're not, because then I don't have to wait 10 minutes. We don't have to do the 10-minute timer each time after each demo. And I can just go through through everything. But you let me know. All right, let's switch to the slides. And the next resource we'll talk about is the secrets. So secrets in Kubernetes they're similar to config maps. And just like with the config maps, you can use secrets to store the key value pairs. You can also mount them into your containers, either as files in a volume or use them as environment variables. However, you should not be really using them as environment variables. Now, the choice between, should I use a config map or should I use a secret? I think it's fairly straightforward. Like if your value is storing, like if you're storing any sensitive information, store it as a secret. That's it, right? Otherwise, store it in your config map. If you're not sure, I guess store it as a secret just to be really safe. Now note that the resource values of the secret are stored encrypted in etcd. So etcd is that key value store that uses the Kubernetes uses to store the objects and the state of the object. However, if you have access to the cluster and if you can list and view the secrets, they're actually stored as base 64 encoded values, and we'll see that in a lab. However, they are encrypted in etcd. So there are three types of secrets that you can create. First one is a generic one, and the secret can be created from either from a file, directory, or a literal value. So this is the key value pair. That's the generic secret. Then there's a secret called secret type Docker registry. And this one is specific for use with Docker registries. So if you're using any private Docker registries, for example, and you need the username and password, you need the auth information for that registry, you could create a secret, a Docker registry secret, and then mount that secret into your pod as a secret to be used when the images are being pulled. Finally, the last type is the TLS, and that's the secret that holds the public and private key pair. Now, as I said, even though you can use secrets as environment variables, it is not recommended because it is very easy to expose them unintentionally. And I gave an example of like when you're logging, right? Or if your application, just before it crashes, it might write all the environment variables to a log, right? And just to be on the safe side, use volumes and then mount secrets as files into your pods instead. So mounting them as files is actually the preferred and a more secure way of consuming the secrets than just using them through the environment variables. So the way to do that, the format looks very, very similar to how you would do it with ConfigMaps. So instead of using a config map, you would use a secret and a secret name, and then the volume mount is exactly the same. You specify the name of the volume, the path you want to mount the files in or the secret in, and then specify if you want to make that those files read only or not. Okay, so that was fast. Let me switch to the lab. Like functionally, secrets and config maps, they're pretty much very, very similar. The way you create them, the way you consume them, right? It's just they're used for different purposes. Okay, so let's create a secret, a generic one. Create secret, generic, service auth, and we'll use the from literal flag, and we'll say username equals Ricky, and then from literal, and we'll say password equals I love pizza 2. Let's do that one. So we have the service auth secret created. If I list the secrets, you'll notice I have the service auth secret here. I do have this one as well, and this is the one we'll use later on in one of the demos. And then there's a service account token as well, and we'll talk about service accounts hopefully next time. I think we'll mention what the service tokens are, service accounts are, and how to use them. Anyway, so the secret is here. Of course, we can describe it, service auth, and you'll notice that it's not gonna show you the value here. So what you can do is you can do a get and then show the YAML representation, and you'll notice that it is base 64 encoded. So if I would do base 64-D, you'll notice that it'll actually decode the values, right? So having it in base 64, what that does is allows you to not just store the plain text values, but also binary data. Now, if you can also create a secret through by creating a YAML. However, if you create it in YAML, you will have to base 64 encode all of your binary values. Now, if you have any values that don't need to be base64 encoded, like something that's not binary and a binary thing, then you can just provide them in plain text using the string data field. So let me show you that. So this is the same, same secret as before, but this time I'm providing the username here under the string data, and then I'm still providing the password as a base64 encoded string. So if we create this one, and then look at the service auth-2 YAML representation, you'll notice that the username gets automatically encoded, right? So even though I provided it in plain text, right, it was still encoded. And then because it was under data, the password was set under the data field. Kubernetes knows that this is supposed to be base64 encoded, so it's not touching it anymore. Okay, so let's show how to get the secrets through as environment variables, secret key ref. This is pretty much the only difference between like a config map and the secret. In the case with the config map, we use config map ref, and then over config map key ref, and over here we're just using secret key ref, referencing the name of the secret and then the actual key from within that secret that we want to mount as an environment variable in this container called secret. So let's create this. Should be fairly fast. There we go. So if I just secret pod, and I'll just run the env command, and you'll notice that the username and password, both of them are set as environment variables here. Okay, so let's delete this. Oh, delete pod, secret pod. I guess I had a typo. Okay, now better way to do this, to mount the secrets, is of course to mount them as volumes. So let's show an example of that one. As soon as this pod is deleted, let me secret pod 1. Okay, just copying the YAML here. Let's apply. Okay, so defining the volume, instead of using the config in config map name, we're just referencing the secret by its name, calling the volume auth secret, and then mounting it under var/var/secrets inside this this container. I think I mentioned, but you can only mount config maps and secrets to the pods that are in the same namespace. So if we had this service auth secret in a different namespace, we wouldn't be able to mount it in this pod. Okay, and then if I go inside the secret pod 1, env, oops, sh. There we go. And then we go in our var, and you'll notice that there's a secrets folder here, and we have the password and we have the username. So if we list the password here, actually contains the value, and then same for the username. So Kubernetes will base64 decode those values, and they'll be stored as plain text inside your container, rather on a volume that's mounted inside your container. All right, this brings us to lab number 2, secrets. And I'll give you another 10 minutes, and then we will continue to init containers and container patterns. All right. I was just looking at the clock, and it's exactly 1 hour. So as if I had planned it to be exact 1 hour to go through secrets and config maps. All right. Since there are no questions, I'll assume that you're either still going through the labs, or there aren't any questions, which is both is good. I'll continue with the container patterns, because we do have, like, I think 4 more. Is it 4 or even 5? No, we have 4 more labs to go through. And I want to give you the opportunity to ask questions as well. Okay, so let's go to container patterns and let's talk about container patterns. So I'll talk about init containers first, and then I'll mention the three patterns, the sidecar, ambassador, and adapter pattern, and give you a couple of examples. I do have labs and demos for sidecar, ambassador, and init container. I don't have anything for adapter, but you'll see it's fairly straightforward. Okay, so let's start with init containers. Okay, so init containers allow you to separate your application from the initialization logic and then provide a way to run some initialization tasks, such as, let's say, setting up permissions, setting up database schemes, seeding the data for the main application, etc. So that's what init container allows you to do. It allows you to run those tasks before your actual main application or main container runs. The init containers may also include tools or binaries that you don't necessarily want to have in your primary container image or primary application due to security reasons, right? So you also want to minimize your attack area. So if you want to do any initialization or anything that you do like a one-off, right, before your application starts, why would you want to include that binary in your main app? You should move it into a separate container, let that init container handle that, and then let your app be app and just run what it needs to run, your business logic. So the init containers, there can be multiple, and they're executed in sequence before your application container starts. So if you want to do this logic with the app containers, if you want to do like initialization and have multiple containers, that's not going to work because the app containers don't have a deterministic startup order, right? One can start before the other one, right? So you can't really use them to do any initialization type of work, right? So that's why you would use these init containers. So they would start first, they would execute first, and then your app containers would start. So the app container will actually wait for the init container to complete successfully before it starts. So in case the init container fails, the pod will be restarted, right? And that will also cause the init containers to run again. Now, this is one thing that you have to keep in mind when you're designing your init containers. You have to make sure that they are idempotent so that they can run multiple times without any issues. So let's say you have an init container where you're seeding your database, right? What you don't want to do is, if your init container fails, you don't want to reseed the database with the same data over and over again if it's failing. So what you need to do is, instead, to make your init container idempotent, make sure that if the data has already been seeded, you don't have to do anything, right? Otherwise, if it hasn't, then do the work. Now, in the first hour of the first session, we talked about pods, right? And I mentioned how the pods share the volumes, the network security settings, resource limits, right? Just like and all that between each other, the containers within the pod. And init containers do the same, right? So this allows you to download some things, prepare some things, configure some things, and leave it in the volumes, for example, for the main application to use. So this is an example that I'll show a demo of as well. And in this example, what we're doing is we're using an init container. Notice line 2, the field is called init containers. You can have more, it's an array. So what we're doing here is we are creating a container called clone repo that uses the Alpine Git image. And within that image, we are running a git clone command. So we're cloning that specific GitHub URL to a folder, share nginx HTML folder. And then we're also, line 19, we're jumping a little bit, we've defined an empty volume. So think about volumes. We haven't talked about them yet, but just think about them as folders that get attached to your pods. So we've created a volume called web, which is an empty folder. And then we're referring to that volume on line 10. So in the init container, when the container starts, we run git clone. We clone that specific repo to share nginx HTML. And this is the same place where we actually mount that volume that we've created, right? So we're basically saying store the contents of the repo in that folder. Then on the line 13, so once the init container is done executing, what we have is we have a repo cloned in that specific folder. Then the nginx container will start, and that nginx container will mount that exact same volume at that exact same path. So that's the actual path that nginx proxy also looks at, right? So what the nginx is going to do when it starts up, it will actually host that index.html from that folder that originally came from the GitHub repo. So let's see this in a demo, how it looks like. Okay, so I will create that exact same pod as we saw in the slides, and we'll just go through it quickly again. Okay, so up here in init containers, this is where we are defining what we want to run before our main application runs. We're going to clone this repo to this specific folder. We have an empty volume defined. It's called web. So we're cloning that repo to this specific folder. So once this is completed, the main container will run. This is our application container, and it's going to mount that same volume under this specific folder. So the nginx will know where to look at for that index.html file. And let me just switch to the repo here. It's just a single index.html file, and nginx will just host this HTML file. That's it. Okay, so let's create the pod, and then I'll list the pods right away. And you'll notice that there's 0 init 0 out of 1 here, which is basically saying that we have a total of 1 init container, and then 0 of them have completed so far. So in case this would fail, if the init container would fail, this would show init error, right? Or it will show crash loop back off if the container fails multiple times. But when it succeeded, the init container completed successfully, and then the website is actually up and running, the website pod. So let's describe pod, describe website, describe this one. I move this up a little bit. So you'll notice that the first thing that happened was that pod was assigned to a node. Then the git image was pulled. The clone repo container was created. So this is the init container. Then the clone repo container started. It cloned the repo. Then the nginx image was pulled. And then finally the nginx container was created and started, right? So this is how it went in order. So let's also look at the logs website. And then using the -c, you can specify which container you want to see the logs from. So I'm saying -c clone repo. I want to see the logs from the init container. And if you've done any work with GitHub and Git, this is how it looks like when you clone the repo, right? So it's just saying cloning the repo into this specific folder. And then the most interesting thing that we can actually do to see that this works is we can use the port forward command. And what this does is it will just create a tunnel from, in my case, from the Cloud Shell inside to this specific pod on port. So I want to expose port 8000 from the Cloud Shell to tunnel to port 80 on the pod itself, which is going to get me to the nginx container. So if I do that, and if I do the web preview, let me change the port to 8000, change in preview. And you'll notice I have the welcome to simple HTML page and I have a hello here, right? Now, if I would make any changes here to this file, I'm not going to see the changes here because I would only see the changes here if I would restart the pod, right? If I would recreate the pod, because that's when we do the cloning. Later, we'll show how we can run a Sidecar container that automatically checks the GitHub repo for changes, pulls them, and then we can always have the fresh website whenever we make a change. Okay, so I'll delete this, and then I'll give you 10 minutes to go through the Init containers lab number 3. And once we're done with that one, we'll talk about the Sidecar containers and other containers. All right. All right. That's a good question, Nikolai. If so the question is if you would create your application in such a way that it's listening to settings file changes and then reloading them as necessary, or just redeploy the container and the settings will be picked up anyway on startup. I mean, writing new code is always risky, right? But people like to do it. So I would love to write that logic and everything, but then again, I think it would be simpler if you just rely on the Kubernetes functionality, because you know it's there, right? And then it's of course assuming your pod doesn't take like 3 minutes to start and restart, right? That would be then much easier and better. Okay, let's move to the Sidecar pattern now. So what Sidecar pattern or Sidecar container aims to do is to it tries to add some functionality or augment an existing functionality without actually changing your main application container. So if we compare it to the Init container, the Sidecar container will start and run simultaneously and alongside your application container. So it's just a second container that you have in your pod, and the startup order is not guaranteed. So you cannot say that, oh, my Sidecar container will be first, and then the application container will start second. Now, if you've heard about the Sidecar container, one of the most popular implementations is in service meshes, in Istio service mesh. So in that case, the Sidecar container, which is the Envoy proxy, runs next to every application container, and then what it does is it intercepts any calls that are being made to your application, as well as any calls that your application makes to the outside. Now in this scenario, this Sidecar container adds the functionality to the existing container, and then the Envoy proxy, what it allows you to do is to do traffic routing, inject failures, and a bunch of other features without modifying your application. So your application has no idea, right? A little bit of a simpler idea might be to have a Sidecar container called log collector, for example, that collects and stores the application's container logs. That way, as an application developer, for example, you don't need to worry about collecting and storing your logs. You only need to write your logs to a location, a volume that's shared between the containers. And then the Sidecar container can then collect the logs from that common volume and send them to further processing or to archive them, right? So your application has no clue, right? Your application is just writing logs as it would write logs anyway, but then there's this extra container Sidecar that's running next to your application that has this additional logic or adds this additional functionality. So if we continue with the example we used for the Init container, what we could do is we could create a Sidecar container that will periodically run git pull command and then update the repository, right? So for this to work, we keep the initial Init container, right? So the Init container will still do the initial clone, and then we'll have the Sidecar container that will periodically run, in this example, every 60 seconds, to check and pull for the changes. So in this listing here on line 7, I've added a container called refresh, and it's using the same Alpine Git image, and it's running a watch command that sleeps for 60 seconds, and then it runs the git pull command, right? So every 60 seconds, it will run the git pull command. Now, another field that might be new here is on line 13, and this is called the working directory. And what this will do is it will just set the working directory of the container. So we're setting it to that user share nginx HTML folder. This is where we originally cloned the repo, sorry. And then we're just running git pull in that repo every 60 seconds. That way, it's just refreshing the repo every 60 seconds. All right, so I'll skip this right now. I'll do the lab later, but let's talk about ambassador pattern as well, and then I'll do the two demos together. So the idea behind the ambassador container pattern is to hide the primary container's complexity, right, and provide a unified interface through which the primary container can access services outside of the pod. Now, these outside or external services might present different interfaces and have, looks like this is not the right image here. I messed up something here. Yes. This does not look good. It's good that I know this. Let me see if, oh, actually I do have another slide coming up next here. Yes. Yeah, so here's an example of, actually, yes, this is an example of how the ambassador container would look like, right? So, so instead of writing the code inside the main container, in the MyApp container, that will deal with some external services with interfaces and APIs, we could implement that logic in the ambassador container, right? That ambassador container has that specialized knowledge then and knows how to talk to an external service and how to interpret responses from, let's say, different endpoints, and then pass them back to the main container. Now, the nice thing about this is that this ambassador container can be then reused, right? So if you have any other number of applications that might use the same functionality, you can just put that ambassador container next to your application, and then your application can call through that. So an example is, for this one would be, and this will be in the demo as well, where I have an application that calls to themoviedb.org. It's just an API with all the movies, right? Now what I could do is I could implement the way to access that API and everything inside my application, right? So I could create the interfaces, right? I could create how to do the authentication with that protected API because it needs like a key and everything. However, instead of implementing that in my application, right, I created a separate ambassador container, right? And that ambassador container will attach any needed like authentication information or anything else that's needed to actually make a request to the MovieDB. So the fact that these two containers are running inside the same pod, from my app, I can actually call the ambassador container through localhost, right? So I could do localhost. I think we have port 8080/movies, and that would go through the ambassador, and then ambassador would actually attach an API key and do anything it needs to do in order to reach the external API, and then it's going to respond back to the My App. So this is how it will look like, the ambassador container. It's just another container that's inside the pod. It starts on line 7. On line 9, I'm just bringing in the API key because that's the API key that's needed to access the movie database. And then I'm exposing the ambassador on container port 8080. So that means within my main container, I could do curl localhost :8080/movies, and the call would go through the ambassador container. It would attach the API key, and then it would call to the MovieDB. oops, go forward. So for the ambassador container pattern, we said that it hides the outside services complexity, right? So think about the complexity of the movie database API, right? So we hide that and we provide a unified, simple interface to our main container, which is just /movies endpoint, right? Now the adapter container does the opposite, right? So it provides a unified interface to the external services, so to the services that are calling into your application. Now, using the adapter pattern, you can use the common interfaces across multiple containers. A really excellent example of this pattern are the adapters that can ensure that all containers have the same monitoring interface. For example, adapter for exposing the application or container metrics on /metrics path and port 9090. So your application might, let's say, write logs and metrics to a shared volume, and then the adapter can read that data and serve that data up on a common endpoint and a common port. Using this approach, you can then add this adapter container to each one of your pods or each one of your applications that you have to expose the metrics. Another example or another use of this pattern is for the purposes of logging. So the idea is similar as with the metrics. For example, your applications can use an internal logging format, but then simultaneously the adapter container can take that format, clean it up, add additional information, and then serve it up to a centralized log aggregator instead. So you can keep your application logging the way that you want them to log. However, using an adapter, you can expose some common interface. Okay, let's go through a bunch of demos now. The first one will be the Init container. Oh, sorry, the Sidecar container. So let me copy the YAML here. And then we'll get started. Let me just make sure that I don't have anything running. Perfect. Okay. So this is similar to what we have with the Init container. So Init container, we're leaving it in here. And the only job of this one is just to clone this repo to this folder. That's it. Then we have our main application container, which is just serving up whatever's in this path, which will be that index.html. And this is where we're actually made the changes here. We've added this refresh, we're calling it refresh container, as a sidecar. And this one is just watching, waiting for 60 seconds, right? And then running the git pull command in this same folder. So let's deploy this one. And you'll notice that now it's saying 2 out of 2. So this is basically saying that we have this pod has 2 containers and both of them are up and running. So we can look at the logs. So if you just do Kubernetes logs name of the pod, it's going to give you an error because we have 2 containers and we actually have to specify from which logs do we want to see, from which containers. Is it from the Nginx or the refresh container, or is it from the Init container? So this is the Nginx one. This is the refresh one. So notice it says every 60 seconds, run git pull. And down here it's saying, oh, it's already up to date, right? Nothing has changed. Let's do the port forward command here again. So I'll do pod website. Okay. And then let's open it. Preview on port 8000. Okay. And this is the same as we saw before, right? It says, welcome to simple HTTP page. Hello, right? I'll open another window here, another terminal. And then we'll look at the logs from the refresh container. And I'll just do -F to follow the log, so I don't have to refresh or rerun the command each time. Okay, so now this is running. We have the website, right? The sidecar container will run git pull command every 60 seconds, right? Regardless if there are changes or not. So I'll go to the repo. By the way, you can try this out as well. You will have to fork this repo and then in your YAML actually point to your fork, not mine, because you won't be able to make changes like this. So let's replace that hello with hello world and a bunch of exclamation marks. So I'll commit the changes. And then I'll refresh the page here. So nothing will happen for, maximum of 60 seconds, right? So we have to wait for the 60 seconds actually to, for the git pull command to run. And once it runs, what it'll do is, because we made changes to the repo, right? We made changes to this HTML file. It'll pull down the changes. And then because Nginx will automatically reload and everything with that file, we'll see the changes here as soon as that happens. So let's wait for a couple of, hopefully not too long for this to happen. And we should see the changes soon. Oh, I don't want to refresh this. Oh, there you go, right? So you'll notice that this is referring to the repo. It says it's updating a different SHA, right? One file was changed. There was one insertion, one deletion, right? Whatever, right? But you see that the file was changed. This is what the sidecar container did. It pulled the fresh file. So now if I refresh it here, you'll see that it says hello world, right? So this is just a very simple way that you could automatically update your website whenever you make a change to your repo, right? A very, very, very simple way to do it. All right, so let's clean this, delete this page, this pod, delete pod website, and then we'll do the ambassador container demo next. Okay. So as I said, I'm using the MovieDB here. If you want to try this out, go to themoviedb.org, I think. I think the link is in the, it's on the Notion page, right? If you go there, you can register for free. You can get the API key, right? So you'll be able to access their API with that key if you want to try this on your own. Okay, so this is deleted. All right, so this is how it looks like if I just make a request to, right, directly to the API MovieDB, discover movies, right? It's saying invalid API key, you must be granted a valid key. So I didn't create the, I didn't provide the API key, so of course I can't get the response back. Now I've already created a secret called the MovieDB here, and there's a command for you that you can use. You can just use the -- from literal and create that secret with your key. And then we will create our pod that will have 2 containers. So the first container will just run the busybox, will just be the busybox image, right? It's not gonna do anything, it'll just sleep, right? This is just so we can get access to it and then run curl from within there. The second container will run this ambassador image. And what this one does is it listens to port 8080, and I'll be able to send a request to that port with the path movies without providing any API key, without even knowing that there's an API key, right? And then this ambassador will then, the container will then attach, it will attach the API key to the request. It will make a request to the MovieDB, and it will actually return the response. So we'll get the response back as if we were authenticated. So let's create this one. So it's saying this container is creating 0 out of 2 ready. So as soon as these 2 guys come up, I'll take a couple of seconds. I think it's because I have a clean cluster. And it's pulling the images again, probably. By the way, for that previous demo, the sidecar where it pulls the repo, I think if you go to learncloudnative.com, I think I wrote an article that uses a more sophisticated script, not just wait for 60 seconds and pull. If you want to use that to play with that. Okay, so we have the movie DB pod up and running. Now what I'll do is I will, the movie DB, and I'll go to the main container, not the ambassador container. And I'll just do bin.sh here, right? So I'm inside this main container, right? And if I would try to curl directly to that movie, right, URL, it's saying invalid API key, of course, because I didn't provide an API key. Now, we know that we have the ambassador container running, and we know that the ambassador container is listening on port 80/bat/movies, right? So from within this main container, we could actually curl to this guy without any API keys, and well, I mean, we get back a response. I'm not gonna parse it, it's a JSON, right? For, I think it shows like top movies, top X movies or whatever, from that website, right? So let's say someone creates this ambassador container, right, that has a simplified interface for you to access, let's say, the movie database, right? It has a simple way for you to provide your own API key, right? So the only thing that you need to do from your application, if you want to access this, is just bring that extra container in. You don't have to worry about parsing the responses, right, or doing anything special. You just call the, as I did, localhost 8080/movies in this example, and get let the ambassador container handle the authentication and the API keys for you. All right, so this is these are demos 4 and 5, or labs 4 and 5. So we'll take 10 minutes, and then we'll be back and we'll talk about application health as the last thing for today. All right, I posted the link to the article that I wrote on how you can build your own Netlify-like deployment for your React apps using multi-container Kubernetes pods. I did notice that there's some rendering issues that I'll have to fix. So, but anyway, yeah, this is a little bit more involved example that has a more advanced type of polling logic and everything, right? And it works with anything, right? You just put the repo in here, the poll interval, and it's gonna dump the build output to a specific folder, and then you can have a separate kind of an Nginx or anything else that will just serve up that the contents, right, as a website. All right, let's go to the last section for today, and this will be about application health. So the kubelet component in Kubernetes uses different health checking mechanisms to verify if the containers inside your pods have either started, so that's the startup probe. Are they ready to receive traffic? That would be the readiness probe. And if they are healthy, that would be the liveness probe. Now note that all these things, how do you know if the container is healthy, or how do you know if your container is ready to receive traffic, or is it ready to start? Has it started? This is something that you will have to decide. As you're writing your application, you are the one who needs to say, this is how I determine that my application is ready, alive, and it can receive traffic, for example. Yes, separation of concerns for the container privacy. Exactly, right? You don't have to mix everything in one big ball of mud, right? Separate these utility-like things into separate containers and do it like that, right? So you can just compose your applications. All right, so startup readiness, liveness probe. This is just like a reference. I think I have it in the walkthrough or in the labs as well. So I've created a Docker image that can, with these different endpoints, that can simulate different things, and this is what we'll use in the demo. So you can use these endpoints, and you can set a couple of environment variables, and then you can simulate different failure scenarios, right? So you can test out how these different health probes can help you out. So the /healthy one will just return an HTTP 200. However, if you have a specific environment variable set, it will sleep. Like it'll sleep for 5 seconds, and then it'll start returning the 200. Health Z will only return 200 for first 10 seconds, then it'll start failing. So this is to simulate application running, but then application like failing for some reason. There's also the ready and ready Z with different like modes that allow us to test all these different probes. So how can you determine, or what are the methods that you can use to determine if your containers are healthy or not? So this is the way that the kubelet can do the things, right? But you, as the application developer, application owner, you'll be the one that has to decide what does it mean for my application to be healthy. So the first way that you can do it is you could run or invoke a command inside of the container, and then the exit code from that command will determine if the probe has failed or not. So if you return a non-zero exit code, that means that the container is unhealthy. The second way is to just open a TCP socket. If the socket opens successfully, the probe is successful. If it doesn't, the probe will fail. And last one is you can send an HTTP request to the provided URI, and then the HTTP response code will be used to determine if the probe succeeds or if the probe fails. The way that you would usually do this is you would implement /health endpoint in your application. So the liveness probe can then call this /endpoint on your application, and then based on the response code, it will determine if your container is healthy or not. So with the combination of these three methods and all the different probes, you can make sure and ensure that your containers are healthy, that they can receive traffic, and that they will actually get restarted in case of a deadlock as well, right? Okay, so let's talk about the first one, the application liveness probe. So this probe indicates whether your application is still working as it's supposed to be. In case of this, if this liveness probe fails, let's say you return a non-200 from the healthy endpoint /healthy endpoint, the kubelet will restart the failing container. So without this probe set, so up until now, we haven't been setting these liveness probes. So Kubernetes just automatically will assume that the containers are healthy and that the pod is healthy and will keep it running. Now, using this probe, what you can do is you can handle the scenarios where your code is deadlocked or your application is not responding anymore, right? If you have a kubelet or some external thing probing and calling some endpoint in your application, and if that it's not responding, you know that something went wrong and the kubelet can restart it. Now, if you didn't have this probe, Kubernetes will just keep the application running even though the application might not be responding, right? If you provide the probe, if the probe doesn't respond, Kubernetes will restart the container, right? So it'll start fresh. So here's an example of how you can define a liveness probe. In this example, so look at line 5. This is where we define the liveness probe. And in this case, we are using the HTTP GET request. So we're saying, kubelet, send the HTTP GET request to the health Z endpoint on this pod on port 3000, right? So Kubernetes will consider this container healthy as long as the response will be more than 200 and less than 400, right? So in our example, the health Z, we will be returning HTTP 200 for the first 10 seconds, and then we'll start returning 500 afterwards just to simulate the probe failing. Now, there are other two settings on lines 9 and 10. The initial delay seconds, this field will just tell to Kubernetes to wait for 3 seconds before you start calling the /health probe, right? So this is just to give time for the containers to start up. Similarly, the period second on line 10, this is just telling to Kubernetes to perform this probe every second. So every second, Kubernetes will call this health Z endpoint and determine if it's healthy or not. So the first probe will be performed in the 4 seconds, right? In the first 4 seconds after the container starts. So this is the initial 3 seconds and then plus period 1 seconds. And then every 1 second after that. Now over here, we're just specifying the path, but there's also a couple of other settings that, that we can configure. For example, we can use the HTTP headers field to specify any headers that we want to pass to the probe. So in that case, we can do /health_z, but also include this header as well, right? So that gives you the option in your application to parse those headers and do something with that and return some values based on that. There's timeout seconds, not timeout settings. That should be timeout seconds, which is just saying the number of seconds after which the probe will time out. The default value here is 1 second. So you should consider increasing this value if your health check probe depends on any other services. For example, if you're from within your application, the way that you determine if your application is healthy or not by calling any like third-party services, and make sure your timeout is greater than just 1 second. The next setting is the success threshold, and this is just the number of consecutive successes for the probe to be considered successful again after having failed. For example, if we set this value to 5, the health probe needs to succeed 5 times in a row after a failure to be considered successful again. So the default here and the minimum value is 1. And if you're defining a liveness probe, this value must be set to 1. Finally, the failure threshold. This is the number of times the probe is retried in case of a failure. So if the probe is still failing after this threshold, the container will either be restarted when we're using the liveness probe, or it will be marked as unhealthy if we're using the readiness probe. So the default value here is 3. So if the probe fails for 3 times, the container will either get restarted or the marked as unhealthy. So the default is 3, and the minimum value is 1. So we talked about HTTP. The second mechanism is using a command probe. So with this command probe, what happens is that Kubernetes will run this command inside of your container to determine if the container is healthy or not. So you can create and define what this command is. The difference is here that Kubernetes will run it inside of your container. So if the command will return exit code 0, the container is considered to be healthy. If the code is anything but 0, the Kubernetes will consider the container as being unhealthy. So the reason why you would use the command probe is when you can't run an HTTP probe. So there's an example where, let's say you have a REST API that's running in a container, and that REST API requires an authorization header, right? You can provide that header to HTTP probe. However, you can't really specify, and you don't want to specify the authorization header value in YAML, right? So instead of doing that, what you could do is you could mount the authorization token secret inside the container and then use curl as part of your command probe. So this example on the slide shows the command. We're just running curl, specifying some user, some password. You can imagine that either coming from environment variables or coming from somewhere else, and we're just calling localhost 3000/healthz. Last one is the TCP probe, and what happens here is that Kubernetes tries to establish a TCP connection on the specified port. This configuration is almost identical to the HTTP probe, but instead of using HTTP GET, you use TCP socket field, like shown in this example. So this specific example, the TCP socket probe will try to open a socket on port 3000 15 seconds after the container starts. So this is initial delay plus period of 5 seconds. An excellent example of TCP probe would be when you're using a gRPC service. So this is all about the liveness probe. So the next one is application startup probe. So when you're dealing with apps that it can take longer to start up, it might be tricky to set up a proper liveness check that's going to work both for the startup of the container, right, as well as during the lifetime of the container, right? So your container might take longer to start up, in which case the liveness probe might start to fail, right? So for that purpose, what you can do is you can use the startup probe that uses any of the methods that I mentioned, HTTP, TCP, or command. However, you can set a higher failure threshold, right? So that higher failure threshold is then for cases where your application takes a long times to start. So let's look at an example. So in this example, the container will have maximum of 2 minutes. So 30 from the failure threshold setting, that's multiplied by 4 seconds from the period field. So lines 10 and 11. To finish the startup, right? So the formula to calculate this is you're doing the initial delay seconds plus what is the failure threshold times the period second, right? So if the probe is failing for the first 2 minutes, Kubernetes won't restart it yet. It won't do anything yet, right? However, once those 2 minutes pass, the startup probe, if it's still failing, the startup probe will be considered as failed. If the application starts up within the first minutes, with the 2 minutes, the liveness probe will take over and it will then ensure that the container stays alive. So the startup probe is just for that startup thing to make sure that application actually starts up. The last one is the readiness probe, and you can use the readiness probe to determine when your application is ready to start receiving traffic. So in some cases, applications might take a while to start up, right? And that could be either because they depend on external services for startup, or they're loading like a considerable amount of data, something that takes time, right? During this time, not just that you don't want to restart the container, right? You don't want to send any requests to the container either, right? So if the readiness probe determines that the container is not ready yet, Kubernetes will mark that pod as unhealthy and won't send any traffic to it. So your container might start, it might be initialized and everything. However, it's not necessarily ready yet to receive any traffic, right? So the Kubernetes will mark this pod as unhealthy. However, it will not restart the pod. It will invoke the probe based on the settings I'll show in the next slide, right? To determine when the pod is ready to receive the traffic. So once that probe succeeds, the readiness probe succeeds, the pod will be marked as healthy and it can start receiving the requests. So here's how the readiness probe looks like. Very similar to the liveness probe. We're sending a GET request to /readyz port 3000, and we have the period seconds and the initial delay seconds as well set for this one. All right, so let's go to the last demo, or last demos of the day. Switch to my Cloud Shell. Now we'll go through the application health. I also included that endpoints reference in there, so you can, if you get that image, you can play with it, right? You can set different values, you can set different environment variables, and you can test out how all these different probes behave under different scenarios. Okay, so let's do the liveness probe first. So I'm creating a pod. This uses this app health thing that has all those endpoints defined. And we're setting the liveness probe on /healthz endpoint with initial delay of 3 seconds and a period of 1 second. So the healthz, what will happen is that this endpoint will return HTTP 200 for the first 10 seconds. And then after 10 seconds have passed, it will start returning 500. So we'll see that the probe will start failing and that the Kubernetes will actually restart the container. Okay, so it's being created. So let's describe, get pod, what was the name? Describe pod liveness. So it started the container, and then I'll keep refreshing this. There you go. So after 10 seconds, if you notice here, it says that the liveness probe has failed with status code 500 because the healthz returned 500. So the container failed the liveness probe. It'll be restarted. So it killed, and then it restarted the container again, right? So once the container is restarted for the second time, the same thing will repeat itself, right? It'll take 10 seconds, it will be all good, and then after 10 seconds, it will start to fail. It will return a 500, and Kubernetes will restart the pod again. So just wait for the second time to happen. Oh, actually, sorry, it's already happening for a third time, time 3 here. And you can also see this. You can see the number of restarts in the restarts field. So if you list the pods, you'll see the number of times that pod actually restarted. So now it's in the crash loop backup state, so it will take longer to start up. So the other thing that you can do is, so in addition to just specify the port and the path, I mentioned you can also specify the headers. So in this example, exactly the same, healthz, but we're also setting this arbitrary header called host with the value liveness host, right? So if we create this one, and this will behave the same way that the previous pod did. It will be healthy for 10 seconds, and then it'll start crashing. So let's look at the logs. You'll notice, and this is just being logged out from the application, right? You'll notice the host header is being set to the liveness host. So this is what we've set in that YAML. And you see that the user agent is actually kubeprobe. So this is what's calling the container to determine if it's alive and healthy or if it's not healthy. And then you'll notice down here, it actually started to fail and it returned a 500. So that was liveness. Let's look at the readiness one and create a separate pod for this. So we're using the readiness probe here, HTTP again, but this time we're using readyz endpoint. And this readyz will return 500 for the first 10 seconds. So it will fail. It will simulate as if the container is not ready for the first 10 seconds. And then after that, it will start returning 200s and it will be ready. Let's do this one. Okay. Now let's describe the pod readiness. And you'll see here that under conditions, it's saying that it's initialized. However, ready is saying that it's false, right? And then after 10 seconds, the ready switches back to true, meaning that the container is ready to receive traffic. So we can also look at the logs. It's logs, readiness. And you'll notice that the readiness pod will not fail because it only fails at the beginning. So if I scroll up here, hopefully I can scroll. There you go, right? So these are the first X requests that were made. And the first of them for 10 seconds, it was failing. And then after that, we all got 200s and application was ready. So you can then use this readiness probe together with the liveness probe to basically health check and ready check the same containers. And then using both probe, you can make sure that the Kubernetes will restart the failed containers when they're unhealthy, but also allow them to receive the requests only when they're ready to receive the requests. All right, so let's take 10 seconds, 10 minutes. If you guys want to go through the application health, or if you have any questions, I'll start the timer for 10 seconds, 10 minutes, and then we'll be back and we'll close it out for today. All right, this was it for today's stream. Next week, I think that might be last time. I think I'll see how much material there is. It'll either be last time or one before last, but we'll definitely need to talk about volumes and how to run stateful applications, as well as the security portion, things like service accounts, role-based access control, RBAC, network policies, and then finally CRDs. If you have any ideas for any other topics you want me to cover, comment on the video, and we can have some more live streams later on. Thank you very much. Subscribe to the channel, like the video, and I'll talk to you next week. Bye.